All right, so we're going to start by looking at chapter 5. And again, this is the last chapter that we do before we're going to start trig. And this section is on exponential functions. So let's graph those two, take a look at them, and see how they look. Anybody have a guess which one is the exponential one? Yeah?
The first one.
So the first one, that is a quadratic. So that's not exponential. So it's the second one. So x squared, that would be, in a more general case, that's a polynomial. But specifically, it's a quadratic. So if we graph x squared and 2 to the x, okay, they look completely different. Okay, there's your x squared. And there is 2 to the x. So if you notice, they both curve up very sharply as you start to head to the right. And if you set the window higher, like around maybe 60 or so, you'll see that one of them starts to curve up a lot faster than the other. So there's your parabola. And the red one is going to curve up very fast. Looks like the parabola does curve up a little bit faster at first, but eventually the red one gets steeper faster. Okay. What do you call this? Like the 2 or the x, because it's below an exponent. Well, it's a variable in one, but not in the other. Yeah?
Is it the coefficient?
No, coefficient is the number that's in front of a variable. Yep.
Is it the base?
The base. Yep. So we have a base and we have an exponent in each of those expressions. The difference is in the first one, the base is a letter, the exponent's a number. In the second one, the exponent is the letter, and the base is a number. Having a letter in the exponent is part of what makes something exponential. We'll talk about something else you need to have too. But 2 to the x is an exponential function. In particular, there are two kinds of exponential. There's one called exponential growth, and there's another exponential called exponential decay. Yep. 2 to the x, with the graph in red, that is an example of exponential growth. So when the variable is in the base, and the exponent is a non-negative integer, okay, like the first one. Those are the kinds of graphs we studied a lot in chapters 2 and 3. Okay, chapter 2, I think, was all about quadratics. Chapter 3 was about polynomials in general. Okay, so that is a polynomial. When you switch it, like in the second one, so that the variable is now in the exponent, and the base is a positive number that is not 1. That is called an exponential function. Why do you think the base can't be a 1? What would be wrong with calling this exponential? It has a variable in the exponent. Yep.
Because 1 times itself is just 1.
Right. That's just basically a horizontal line at 1. That wouldn't curve up. Okay, 1 to any power is always going to be 1. So when you have a variable in the exponent and the base is a positive real number, not equal to 1, that is called exponential. So any question on the difference between a polynomial and an exponential? Polynomials can have a lot more different kinds of looks when you graph them. Exponentials really only have a couple.
Are you going to go over what they are?
Yeah, that's one of them, the one in red. And basically, you can just take that graph in red and reflect it over the x-axis or the y-axis. And those would be the other types. But we'll look at two of the types. Okay, so let's say we have an exponential function, like the one in red. What is the domain of that graph in red? Yeah.
X is greater than or equal to 0.
So it never goes to the left?
Oh, I'm thinking, all real numbers.
Yeah. The domain is all real
I
numbers.
was thinking why.
We'll talk about range in a second. But yeah, domain is all real numbers because it does go left and right forever. You can't change that. When you have an exponential, that does not change. And by doesn't change, I mean if we stretch it, shift it, flip it, reflect, nothing you can do to an exponential would ever change the domain from all real numbers. Again, just a reminder that the base has to be a positive real number, not equal to 1. We already said that. And the range. What's the lowest and the highest that the range goes from? Yep.
It's the lowest 0?
And does it look like it reaches 0?
No.
No, it actually never reaches it. If you go to the table and start plugging in numbers that go to the left, all we do is get numbers that are getting closer and closer and closer to 0, but they are never reaching it. Eventually, it's going to start giving them to me in scientific notation. 0.00003. But it never reaches it. What do you call a graph that gets closer to a value, but it never reaches the value?
Asymptote?
Asymptote. Yep. And that's exactly what you have in that red graph. There is an asymptote on the x-axis. Yep. So the range is from 0, and I put a parenthesis because it is an asymptote. You never reach it, to infinity. That can change. Right. So for example, if you did y equals and you put, let's say, 2x plus 10, it doesn't go down to 0 anymore. I just made a change to the range. What do you think the lowest it goes now is? Yeah?
10?
10. Yeah. You shifted it up 10 units. Okay, so the range can change. The domain cannot. So those are all examples of exponential functions. They all have bases that are positive real numbers. 10, 4, and pi, a fraction of decimal bases, those are fine. And they all have exponents that are variables. Those are all examples of functions that are not exponential. Okay, the first one under non-exponential, that's a cubic. It's a polynomial. What kind of polynomial is the second one under non-exponential? Yep.
It's a fraction.
But how would you classify it based on its degree? what is the degree of g of x under the non-exponentials?
4.
4. And what do you call a polynomial that's degree 4? Remember that. Yeah?
Is it quartic?
Quartic, yep. So that's a quartic polynomial. You could also think of it as 1/2 x to the 4th. That's the same as x to the 4th divided by 2. And the last one, that's not exponential. It doesn't have any exponents as variables. So any questions on the ones that are exponentials and the ones that are not? Or do you have like does anyone have an example? They were like, what if you had this and this? Would that be exponential? Something like that. So let's look at the difference between 2 to the x and 3 to the x. Are they both exponential? Why?
Because there's a x, but there's a variable in the exponent as
There's
well.
a variable in the exponent. And what else? Yep.
And the base is a positive real number.
And
Not
the
equal
base
to 1.
is a positive real number not equal to 1. Yep. So they're both exponential. What do you think the difference will be between 2 to the x and 3 to the x? They're both going to look kind of the same.
Slope.
What do you mean the slope?
Like how quickly it goes up.
Yes, how quickly it starts to curve up. The rate of change of the slope is going to be faster in the 3 to the x than the 2 to the x. So that's 2 to the x. 3 to the x is going to start to curve up quicker. Okay, so it curves up a little sharper. And if you did something a little bit smaller, like 1.3 to the x, there you go. That one's going to curve up a little bit slower than all the others. Okay, but those are all exponential, each one of them. So when we're looking at exponential graphs, we always want to try to look at something that has a base and a positive exponent. If they give you something with a negative in the exponent, we need to get rid of that negative. So I'm going to show you how you get rid of it. What is a to the negative first power? If you were to rewrite that without a negative on the a. Yeah?
Is it a over 1?
It's, you said a over 1 like that?
Yeah.
Not quite. It is a fraction though. It is a fraction.
Is it 1 over a?
1 over a. Yeah. So when you raise something to the negative 1 power, it's the reciprocal. It takes it and flips whatever you have. So keep that in mind because we're gonna use that in a second. So let's say we had a to the negative x. That negative in front of the x is going to mess up trying to look at this graph. So we're gonna get rid of that negative. What number is in front of x here, even though it's not written? Yeah. And what does that symbol do to it? Yeah.
Negative 1.
Negative 1. So it's like we have a to the negative 1 times x. That's what that means. But what I want to focus on is this. You're multiplying two things together in an exponent. Does anybody remember, like, if you had something like this? How would you simplify that? Yeah? Yeah, it would be 2 to the 12th. So whenever you multiply two things together, like this, it had to have come from something like that. So now I want to think of what we just wrote down. We have something like this. And now I want to think of it as something like that. So let's go back to it. How could you think of that like I did on the previous page? Instead of a to the negative 1 times x. What would it have been before that step to get that? Yep.
Would it have been a to the negative first in parentheses to the x?
Yeah. It would have had to have been a to the negative first to the x. It would have been a power to a power. And the reason I want to think of it that way is because now we know how to get rid of that negative 1 on the a. What's a to the negative 1? 1 over a. So when we have a negative, where are the x's? The way that you can get rid of it is you take your base and you flip it and raise it to the x. So what if we had, let's say, 3 to the negative x? What do you think that would be the same as? Yeah?
A third to the x?
Would be 1/3 to the x. How about if we had like 5 to the negative x? It would be 1/5 to the x. Yep, that's the pattern. So the reason we want to do that is because when you look at this, you may think, oh, that's a base of 3. No, it's not really a 3. It's actually a base of 1/3, okay? Because that negative is messing it up. So we always want to get rid of the negative so it's easier to think about. River, is that yours? Yeah, thanks. Because when the base is smaller than 1, I mentioned this term earlier, decay, you're going to have what's called decay. When the base is bigger than 1, you're going to have growth. All right, so we've got to make sure we know what the base really is. All right, so let's look at this one. I want to graph these two, and then we're going to look at the domain and the range. Let's start by fixing that one so it doesn't have a negative. Nick, could you tell me what g of x would be if you get rid of the negative with the x?
It would be 1 over 2 x.
So you get 1 over 2, and then what comes after that?
The parentheses, and then it would be to the power of x.
Yeah, perfect. To the power of x. Yep. Okay, let's graph each one of them. All right, so we've got 2 to the x and 1 over 2 to the x. Let's do zoom 6. Okay, that's the one we've already done, 2 to the x. And now watch the 1/2 to the x. It's actually going to be a mirror image of the one in blue.
Oh.
It's a mirror image. So now let's look at that. Yeah, yeah, it's a reflection over the y-axis. Everything's kind of reversed. So let's look at, let's see, f of x was 2 to the x. That's the blue one. G of x was the red one. What's the domain of the blue one? Yeah.
All real numbers.
All real numbers. Yeah. You cannot change the domain of an exponential function. It's always that. How about g of x? Yeah.
All real numbers.
It's also all real numbers. Okay, the red one goes left and right forever. I know it looks like the red one goes up as you go to the left, and it does. It goes up, but it does keep going to the left. And now let's look at the ranges. Let's start with the blue one. What's the range of the blue graph? Yeah.
Parentheses, 0, comma, infinity.
Yep, never reaches 0, but that is the lowest for the blue one, and the highest is infinity. How about the range for the red one? Yeah.
0, comma, infinity.
It's also 0 to infinity. So the point is you can have two exponential functions that each have the same domain, same range, but they look different. The one in blue is growth, the one in red is decay. Okay, any question on that? Yes?
For the range of g of x, wouldn't it be negative infinity, 0?
Well, to have something that goes to negative infinity to 0, you'd have to have a graph like this.
Okay.
That would be a range of negative infinity as the lowest, up to 0 as the highest. It would be kind of like a reflection of the blue one. Yeah. Or you could reflect the red one as well. This would also have the same range, like that. So those ones in purple are the vertical reflections of the red and the blue. But yes, that would change the range. Yeah, anything else? Yes?
Does when it's negative infinity, does it always go first in the parentheses?
When you write an interval, you always put the smallest thing first and the bigger thing second. And since negative infinity is the smallest imaginable thing you could have, it would always have to go first in the parenthesis. Yeah. All right, so we just graphed that for 2 to the x and 2 to the negative x. It wouldn't have made that much of a difference if we did 3 to the x and 3 to the negative x. It just would have changed the sharpness of the curve a little. So what I want to do now is generalize what we just said to any base to the x and 1 over that base to the x. But we can still use this as an example to help us figure this out. Okay, so a to the x, that is similar to the blue one. You could just change the steepness if you change a. And g of x is similar to the red one. Again, you could change the steepness if you change a. So as x approaches infinity, so we'll do each one at a time, it's asking you what happens to the y value in every case. So what, on the blue graph, what happens to the y value as x approaches infinity?
Can you ask your question again, please?
So as x approaches infinity on the blue graph, what happens to the y value? Yeah?
It also approaches infinity.
It also approaches infinity, yeah. As x approaches infinity just means as you head to the right, what's happening to the y value? It's going up. How about on the blue graph as x approaches negative infinity? What happens to the y value? It approaches 0. Yep. And that's what always happens with an exponential growth function. As you head to the right, it goes up forever. As you head to the left, I won't say it always approaches 0, but it approaches a number. Right, now let's look at the red one. What happens in the red graph as x approaches infinity? Yep.
G of x approaches 0.
G of x approaches 0. And what happens in the red graph as you approach negative infinity? G of x is approaching what? Infinity. And those two statements we just said are characteristic of all decay graphs. They go down to a value as you go to the right. It might not always be 0, but they go down to a value. And as you go to the left, they curve up forever. So So that's the big difference between growth and decay. And what controls whether you have a growth or decay graph is the base. If the base is a number greater than 1, you will get growth. Looks like that. If the base is between 0 and 1, like a half, a third, 0.7, anything between 0 and 1, that is decay. And that looks like that. So is there any question on if I give you a problem on the test and I say, determine if the following is exponential growth or exponential decay, how you would do it? Yes.
I thought you said that decay was less than.
Yep. Yeah, between 0 and 1.
So it can't be a negative?
No. It has to be a positive real number.
So like if it was a negative, you would just like convert it and make a
No.
fraction?
You can't have a negative. It doesn't even work.
No, I mean if it said like a to the negative x and would be 1 over a.
Oh, you mean a is positive, but like
Yeah.
3 to the negative x.
So
Yeah.
you would just switch it?
Yeah, you got to switch it.
Okay.
Yeah. So if you had this graph and you told me this is growth, that's wrong.
Yeah.
So when you're looking at the base, you can't have a negative there. It's got to be of the form a to the x, no negative in front of it. So this is really a decay graph. And then if they gave you something like this, 1/5 to the negative x, that's really growth. Because anytime you have a negative here, it causes this base to flip.
Do you think there's gonna be ones like that on the test?
Like one of these two.
Yeah, where it has like the negative but it flips back.
Yeah, you could have a negative in front of the x, yeah. So the first thing you always want to do is get rid of it. Yeah. All right, let's take a look at transformations. Okay, the nice thing about the stretching, the shifting, and the reflecting, there's no difference between this and every other one we've already studied it for. And we've done it at least 3 or 4 times now. Polynomials, we did radicals, we did rationals. Now we'll do exponentials. All right, so let's say we have y equals. We have, well, let me show it. I guess I can show it to you for a specific number. Let's say you had 2 to the x, and you want to see all the transformations you could do for 2 to the x. But remember, this base can really be any number. 3 to the x, 4 to the x, wouldn't change what I'm about to show you. You can add or subtract inside the exponent, that does something. You can multiply inside the exponent, that does something else. You can multiply outside the exponent, and you can add or subtract outside the exponent. Okay, let's start with A. A is adding and subtracting. When you add or subtract, is that a shift or a stretch? That's a shift. And because it's inside the exponent, would it be a horizontal or would it be a vertical?
Is it real?
Well, when we did radicals, what would this do? That's adding inside the radical. Would that shift it 3 units left or right? Or would that shift it like 3 units up or down? This would be left and right. So whenever you do it inside, it's a horizontal shift. So I'm just going to erase this. Horizontal shift. And positive would shift it to the left. And negative? Right. Okay, so that's everything that you'd have to know about A. Let's look at B. B is still on the inside of the exponent, but it's multiplication. So what kind of transformation do you think B is? Yep.
Horizontal stretch.
What is it?
Horizontal stretch.
Yep, that's a horizontal stretch. And remember, it is backwards. So let's just say, example, B equals 3. If B is 3, it doesn't stretch it 3 times. It actually stretches it 1/3. So if B is 3, that's a horizontal stretch by 1/3. What about if B was a half? How do you think you would do that one? That's a horizontal stretch by 2. Okay, and there is one more thing that can happen if B is a negative number. What does multiplying by a negative cause your graph to do? Yep, causes your graph to reflect. So if B is negative, reflect over, that's a horizontal reflection, so that's over the y-axis. So that is everything that the B can do. Now C is very similar to B, but it's on the outside. So what kind of transformation do you think C is? Yeah.
A vertical stretch or shrink.
Yep. So that's your vertical stretch. And this one is not backwards. So let's say you had C equals 4. That's a vertical stretch by 4. Or by a factor of 4. If C is a half, makes it half as tall. The other thing that can happen with C is it can be a negative. So what do you think you would do if C is negative? Yeah.
Reflect over the x-axis?
Yep, it's a vertical reflection. It would look something like this. And that's reflecting vertically over the x. So reflect over x-axis. Okay. So that's everything you need to know for C. And lastly is D, adding and subtracting outside the exponent. What do you think D is going to do? What's
Vertical shift.
Yep, vertical shift. Okay, so we got D, vertical shift. Positive would shift the graph which way? Up, and negative? Down. There you go. So there are your 6 different transformations of this function.
What is the R?
With the plus or minus.
Oh, right here? Yeah. Plus or minus. When you describe them, you do have to put them in a certain order. So make sure you follow this order. Horizontal shift, horizontal stretch, horizontal reflection, which is over the y-axis. Then we go to the vertical stretch, the vertical reflection, and then we finish up with the vertical shift. So A, then B, then C, then D. All right. When you are doing transformations, you'll always compare two graphs that have the same base. So you never compare like 3 to the x to 4 to the x. They're both exponential, but they're different families of exponentials. So these both have the same base. How many transformations do we have? How many transformations would it take to change f of x into g of x? Yep. 3. Yep. 3 transformations. And what number are we going to focus on that tells us the first one? We're focusing on the, yep.
The exponent.
So what number are you focusing on?
The +1.
Yeah, the +1 in the exponent. And can someone tell me what the +1 in the exponent will do? Yep, say the whole thing for me.
Horizontal shift left 1.
Yes, shift left 1. So you gotta make sure you say the direction and how much. Okay, so there's your first one. We have 2 numbers left. Which number are we gonna look at for the next transformation? Yeah, okay. So the -5 is taking the place of the d, and the d is the last one. So we are going to look at the -5, but not yet. Dylan?
Or your x.
So it's a number. So what's the number we're looking at next? The 3 is just the base. So that doesn't have any, the 3 does not do anything transformational. It's just the base. Yeah.
Would be 2.
We're looking at the 2. Yep. And can you tell me what the 2 is going to end up doing?
It's going to be a vertical stretch by 2.
Yep. So that's a vertical stretch. Factor of 2. And now the last number we look at is the -5. And what's the -5 going to do? Yes.
It goes down. It goes down 5.
Down 5.
It
Yeah.
shifts the whole thing.
Shifted down 5. There you go. So there are your 3 transformations. Any question on the transformations? You probably won't have all 6 in the same problem, but you could have 3, you could have 4, but that's generally the most that I do in the same problem. Okay. Okay, so the last thing we're going to look at are some problems that use formulas for exponential growth and exponential decay. So when you have a problem and it says that something is increasing or decreasing by a percentage, that is exponential. So like if you're at work at a job and you get a 2% raise every year, 2%, because it's a percent, is exponential. It's not fast, it's a very slow curve, but it is still exponential. Compare that to working at a job and making an extra, say, $1,000 a year. That's linear. That's just adding 1,000 every year. That's straight line. A percentage over time is always better because it's exponential. In the long run, percentage is better. So when we are doing exponential growth problems, that's the formula that we need to use for our calculations. So you'll have some amount that you're trying to figure out, maybe an amount of people, an amount of bacteria, but it'll be an amount. And the formula is P, which is the initial, times 1 plus r to the t. What is important about r, though, if they tell you that something is increasing by, say, 12%, you need to change the percent to a decimal. What is 12% as a decimal? Yep. Right, it has to be changed to 0.12. Yep. T is usually measured in years, but could be days. I think years and days are the two we're going to see today. Now, if you change one thing in that equation, it becomes the exponential decay formula. Anybody have a guess what would change to make it decay? Yep.
Plus sign.
And what would it change to?
A negative sign.
Yep. So how do you know if something's growth or decay? Well, when you read the problem, if it says something about increasing, that's growth. If it says something about decreasing or going down, that's decay. So we have a town with a population of 50,000 people, increasing at 2.5% every year. Well, is that a growth or a decay? Yeah, growth, because it says the population is increasing.
What's T in that problem?
T is time.
Is it in a specific format?
It can be any unit. Years, in this problem it's going to be years, but we're going to do one in a little bit that's days.
Yeah.
We could do, I think we do one that's hours as well, but any unit. Just as long as they're consistent with the unit. If they say something like you have a town with a population increasing at 2.5% per year, and then they ask you how many people will you have at the end of 36 months, you can't plug in 36 for T. You'd have to change months to years. Any question on that? So you have to use the same unit that they use in their problem. So they want us to write a formula for that situation, graph the formula, and then figure out when we're going to reach 100,000 people. So basically, how long does it take the town to double in population? Assuming a consistent 2.5% growth rate every year. Okay, so we're going to find the amount of people, and it will be a function of t, which is the time in years that have passed. What comes right after the equal sign in the exponential growth formula? Yep.
50,000.
The initial amount, which in this case is 50,000. And then what are we going to put in parentheses next to the initial amount? And remember, whatever rate they give you, you need to make sure it's a decimal. Yep.
1 plus 0.025.
Yeah. 1 plus 0.025. And there's one more thing we need there. We need time, and where's that going to go? As power, yeah, as an exponent. And they didn't say, like, find the population after 7 years. If they said something like that, then I would have filled in a 7 for the time. But the question in this problem isn't about finding a time. I mean, it's not about finding an amount of people. It's about finding an amount of time. So find when the population reaches 100,000. All right, well, let's graph what we have first. Because it says use the graph, so we need a graph. So we're going to type in 50,000. We're going to simplify 1 plus 0.025. Let's just say 1.025 to the x. Okay, let's look at our window. X is the time. You can't use t, you have to use x. what kind of numbers make sense for time? Yeah.
Positive ones.
Positive ones. Yeah, we can't have negative time. And then how much time is going to have to go by to hit 100,000? Well, we could just start with 40 years of time going by, and if that's not enough, we'll do more. Okay, why min? What's the smallest number of people that we could have in this problem? 50,000. Yeah, we can't go under 50. And we want to figure out when we reach how much? 100, so let's go a little bit higher. Let's go to 120. Let's hit graph. So there's our population. Might look a little linear at first, but hopefully you can tell that it is definitely curving. There's a curve to it. And we need to graph something else in y equals. We need to put a line at 100,000 now. All right, and what do you think we have to do now?
Second.
Yep, I'm going to find the intersect. Because there's only two and they only cross in one spot, you just can hit enter 3 times. And there's your answer. So it's going to take 28.07 years. 28.07 years. That's the amount of time for the population to double, assuming a growth rate of 2.5% every year, and 50,000 people to start.
Did you put 2,000 in the graph?
Yes, I did.
Or you put 100,000 in the
Yep. Because we're filling in 100,000 for the amount of people right
graph?
there.
And that's what you put for the y.
Y max, I think I did 120,000. We don't want to do 100,000 because then the red line would be right on the edge of the screen and we'd barely see it. Okay, any question on that one? Okay, so that's exponential growth where they give you a percentage that it's growing by. Okay. When you're graphing, always be careful about negatives. We just talked about that. Negative amounts of people, negative amounts of time, doesn't make sense. Okay. We're going to look at another kind of exponential growth, which is specifically the kind of growth where something is doubling every whatever, every year, every minute, every hour, something doubling.
My calculator didn't give me the second graph. But I
It-
typed it in the exact same
It didn't give you the second one?
No.
Is it turned on? Does it show a black box on it like that?
Yeah.
And you set your Y max to 120,000?
Yeah.
Let me take a look.
You're shot drunk.
Oh, it's because it's 1.025 to the base. I think you have a different number. Okay, so if we had a bacteria, we're starting with 100 bacteria doubling every hour. I want to fill out this table and see if you notice a pattern. How many bacteria would you have at the beginning of the experiment when no time has gone by yet?
100.
100. That's the initial amount. No time has gone by. Now it doubles every hour. So how many bacteria would you have after 1 hour? 200. And then after 2 hours, it will have doubled again.
400.
And again,
800.
800. So it's more important to actually look at this, which is the calculation rather than the result. It's always this number, which was what? The initial, times is always a 2 here. And then the exponent is the number of hours that have gone by. So it's the initial amount times 2 raised to the power, which is the number of hours that have gone by. Now, we might not always have 100 bacteria to start with. So in general, would be something like this. Whatever the initial amount is, times 2, and the exponent is t divided by the length of time to double. Now, the reason that that has to be t divided by the length of time to double is because this exponent right here has to represent the number of doubling cycles. So for example, if something doubled every 10 hours and 30 hours had gone by, how many times would it have doubled? Yep, 3. This exponent has to represent the number of times it needed to double. So if 30 hours had gone by and it doubles every 10 hours, 30 divided by 10 gives you 3 doubling cycles. Now, if the length of the doubling cycle is 1, then yes, the amount of time that goes by and the number of doubling cycles are the same. It's doubling every 1. Okay, so let's try that with this. Okay, suppose that we have 100 bacteria doubling every hour. So this is exponential growth because it's doubling, but you don't have to worry about the 1 plus r. Anytime it's doubling, you always just put a 2 after the initial amount. So what would be the first thing after the equal sign in our formula? 100, yep. So we get the initial amount times, and then what number always comes after the initial amount in a doubling formula? It's always a 2. So that's taking the place of the 1 plus r. It's just a 2. And then what would the exponent be? T divided by length of time to double. Yep. Which would be 1. Because it's doubling every 1 hour. So because it's just a 1 in this case, it really could just be a t. Okay. But if it wasn't a 1, that would be a 1. Okay, let's put that in. So we got 100 times 2. As long as you put a time sign, you don't need parentheses. I just wrote it like that on paper, but you can put the parentheses and it would work the same. Raised to the x. And we're trying to figure out when we have how much bacteria? 350,000. Okay, we can leave the x the way it is. That's fine. What would be a good value for my y min? Yeah, I'm never going to go below 100 bacteria. And what about my y max?
360,000.
Yeah, we should go over, something over 350. So you could do 400, you could do 360, that would be okay. Just go above 350. Let's hit graph. At first it looks like the bacteria is staying flat, but then it really all of a sudden starts to take off. We should get another line in a second. There it is. So our X max was a lot higher than we needed. I think I went to 40. Probably could have went to like 15. It's not that much. Calculate the intersect. And it's going to take 11.8 hours. So if you think about it, that's not that much time to go from 100 bacteria to 350,000. It's going to happen in a little under half a day, 11.8 hours. Any question on that before we look at the last one? So the last one is the opposite of doubling. What's the opposite of doubling? Yeah.
Halving?
halving, yeah. And that's called half-life. So half-life basically measures the amount of time it takes for something to decay to half of its original value. So a lot of times you see that when you're talking about like nuclear or radioactive material. So let's say you had a nuclear power plant and you produce 1,000 pounds of waste today, like 1,000 pounds. If the half-life is, say, 5,000 years, then 5,000 years from now, that 1,000 pounds of waste will then be down to 500. And then in another 5,000 years, it'll go down to 250. And then in another 5,000 years, it'll go down to 125. So it actually never goes away. It just gets smaller and smaller. Half-lives can be really, really long, like with some nuclear waste. That's why it's kind of a problem once you make it, because it needs to be put somewhere for hundreds and thousands of years for it to become safe again. And then some things have an extremely short half-life. So when they make something in a lab, like it might only be around like a millisecond to be able to try to study it. That's not much time. Okay. The half-life formula, it's very similar to the doubling formula. The only difference is instead of a 2, you're going to use a 1/2. The 1/2 is taking the place of the 1 minus r. So normally when you have decay, you do 1 minus r. Well, this is 1/2 because it's half-life. Okay. So we're going to have a substance that has a half-life of 20 days. And we're going to start with 5 grams of it. So how much would be left after 20 days? Yeah?
2.5.
Yeah, 2.5. But it's not decreasing linearly to 2.5. It's decreasing exponentially to 2.5. So you can't say, well, after 10 days, I would have half of, I'd be right in the middle of what I'm going to end up with, which is 2.5, and what I started with. No, because it doesn't decrease linearly. It decreases on a curve. All right, so we know what we're starting with. We know the half-life. So they want us to find a formula and graph. Okay, so let's do the amount as a function of time. Okay, what comes right after the equal sign in the half-life formula?
The initial amount.
Yeah, 5, which is the initial amount. Yep. So 5 grams. What's going to go right next to it for the multiplication? 1/2. And what's my exponent going to be? Yeah?
Would be t divided by 20.
Right, it has to be t divided by 20 because that exponent has to be the number of halving cycles that have gone by. So like if 60 days have gone by, that exponent needs to be a 3. It would have cut itself in half 3 times. Okay, so we want to figure out when we are under 1 gram. Okay, let's put that in. I'm going to do 5 times 0.5, just because 0.5 is easier than doing a fraction. I don't need parentheses that way. Okay, so there's your decay. And we're trying to figure out when we have how much left.
Less than 1 gram.
So yeah, let's put a mark at 1. Let's look at our window. Well, if we only go up to 40 days, that's how many half cycles? It's only 2. So if you take half of 5, that's 2 1/4, or 2 1/2. And then if you take half of that, that's 1 1/4. So 40 days isn't enough time. It's going to take more than that. Let's go to go to 75 days. What would be a good value for the minimum that we're going to approach, but never reach?
0.
Yeah, you'll never reach 0. If you just keep taking half of a number, it never gets to 0. And what would be a good value for the maximum? 5, that's what we're starting with. So there's our decay. We need to get under 1. Yeah, we got it. Okay, so what do we have to do now?
Find the intercept.
Find the intersect. Okay, so there is your answer. Now we have to interpret that. How would we answer the question? When will there be less than 1 gram remaining? Yeah?
After 46.4 days.
Right, you want to be beyond that amount of time. That'll put you in this section right there, where you're under the red line. Okay, so when will there be less than 1 gram remaining? After approximately 46.4 days, which is a little more than 2 half-lives. Any questions on that? All right, so that's everything on exponentials. So looking at domain and ranges, transformations, and growth and decay word problems. So that'll be the homework for tonight. Remember, if we don't have class tomorrow, we will skip 5.4 part 2. If we do have class, then we'll do 5.4 part 2. But either way, the test on Friday will cover whatever we do in chapter 5.